students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for another important session in solid state. Today we shall see the different types of defects in non-stoichiometric crystals. Before that, you should know what are non-stoichiometric crystals, right? What is non-stoichiometric compounds? See, these non-stoichiometric compounds are always called as betholide compounds, okay? See here, the compounds in which the number of positive and negative ions are not exactly in the ratio as indicated by the chemical formula are called as non-stoichiometric compounds, okay? See, the structure will not be having the same number of positive and negative ions. See here, these are the negative ions and these are the positive ions. The number is entirely different, okay? So it will not be the same as that of given in the chemical formula. So those type of compounds are called as non-stoichiometric compounds, okay? For example, ferrous oxide, FeO. This exists in non-stoichiometric form as Fe. See here in FeO, see Fe is 1 and oxygen is 1. But here see the original composition, it is 0.95 and it is 1 and it's called as Woodside. So what do you mean by non-stoichiometric defects? See what is when the ratio of the number of positive and negative ions of the crystal gets disturbed by the defects present in the crystal, then it is referred to as non-stoichiometric defect. Okay. Actually, in such type of crystals, there will be excess of either a positive, that is a cation, or negative, that is anion. Okay. However, the crystal as a whole is neutral in nature. If the positive particles are in excess, then the charge will be balanced by the presence of extra electrons. In case if negative particles, that is anions, are in excess, the charge will be balanced by acquiring higher oxidation state of the metal atoms. Understood? If positive, that is cations, are more, then it will be neutralized by electrons, and if negative anions are more, then it will be balanced by acquiring higher oxidation state of the metal atoms. Understood, students? Next, we are going to see the types of this non-stoichiometric defects. There are three different types. The first one is metal excess defect due to anion vacancy. And the next one is metal excess defect due to extra cations. And the last one is the metal deficiency defect due to cation vacancy. Okay. So now we are going to see one by one with examples, right? The first one is the metal excess defect due to anion vacancy. Okay. So actually how this arises, this defect arises due to missing of some anions from the lattice sites. Okay, some anions will be missing from the lattice sites, leaving holes. Okay, see when anions are missing, see here this is a crystal which is having A plus B minus. Okay, positive cations and anions. If any one of the anion is missing from that lattice sites, it will be occupied by electrons in order to maintain the. So here the one electron is missing, so it is balanced by one electron. Okay, so let me explain this with an example now. For example, let me take a NaCl crystal. Okay, NaCl. Now, let us consider this as the NaCl crystal where A plus represents Na plus and B minus represents Cl. Okay. See, for example, let me explain in the case of NaCl. Okay. See, when this alkali metal halide, that is the NaCl crystal, is heated in an atmosphere of alkali metal vapor. That means when NaCl crystal is heated in the presence of Na vapors, the metal atom, that is the Na, will be deposited on the surface of the crystal. So on the surface of the crystal, this Na will be getting deposited. Okay. So how it will be getting deposited is, see, this Na will be getting converted to Na plus and E minus. Okay. So this Na plus will be getting deposited on the surface of this NaCl crystal. Okay. Now what happens is, see, this B minus, as I told you, A plus represents Na plus. Okay. And B minus represents Cl minus. Okay. Now what happens? See here, this Na plus is getting deposited on the surface when this NaCl crystal is heated in the presence of Na vapor. Now what happens is, the Cl minus, that is B minus, which is present inside the crystal, will be moving towards the surface and it will be joining with this Na plus. Okay. So the Cl minus, which is present inside the crystal, will be joining with the Na plus, which is found on the surface, and it will be forming NaCl and it will be getting deposited on the surface. Understood, students? Now what happens? In order to maintain the electrical neutrality, see when B minus is moving, from this side, there will be a vacancy created. And in order to maintain the electrical neutrality, the electron which is furnished by the sodium will be diffusing inside the crystal and it will be occupying the vacancy created by the Cl minus. Okay. So now this center, the trapped electron, okay, this trapped electron is otherwise called as, this center is otherwise called as F center. Understood, students? This center is otherwise called as F center. So the vacancy will be occupied by the electron which is furnished by the metal on the surface, and that center will be otherwise called as F center. So the electrons trapped in anion vacancies are called as F centers. Okay, they are called as F centers. See, now the presence of this F centers causes color. So this F centers are responsible for the production of color in this type of crystals, and also this is also responsible for conductivity because the electrons will be moving, right? And the magnetic character is also specifically because of this presence of F center. Okay. Now what happens is the electron which is trapped in this vacancy will be absorbing the light and it transmits from the ground state to the excited state. When it absorbs light, it starts to move from the ground state to the excited state. This gives color. Okay, due to the transmission of electrons from the ground state to the excited state, there will be production of color. So in the case of NeCl, the color produced will be yellow. So the this NeCl will be producing yellow color. If it is KCl, then it will be producing a violet color. Okay, it will be producing violet color. And if it is lithium chloride, LiCl, it will be producing pink color. Understood, student? So, this type of defect is found in crystals which are likely to exhibit Schottky defect. Okay. See, already I have explained the Schottky defect in my previous video. See, if you want any clarification, I can give the link for the video which explains the Schottky defect. You can make use of it. Okay, I will be giving the link in my description box. Understood, son? Hope you might have understood what is metal excess defect due to anion vacancy. See, you should be thorough with this F center because you can get questions from this F center and what are the colors, different types of colors produced by the different compounds. So the next one is the metal excess defect due to extra cation. See, actually this defect arises if an extra cation is present in an interstitial site. See here, the extra cation is present in the interstitial site and the electrical neutrality is maintained in the presence of equivalent number of electrons in some other interstitial site. See here, one cation is present in the extra cation is present in the interstitial site, and in order to maintain the electrical neutrality, another equivalent number of electron is present in another interstitial site. Okay, so this type of arrangement will cause the metal excess defect due to extra cation. Understood, students? So let me explain with an example right here. So let me take an example, zinc oxide. Okay, zinc oxide. Okay, now A plus, see here, A plus represents Zn and B minus represents oxygen. Okay, so A plus represents zinc and this B minus represents oxygen. Okay, so when this zinc oxide is heated, it loses oxygen and turns yellow in color. When it is heated, it loses oxygen. This gets converted to Zn2 plus and it gives oxygen. Okay, and also it liberates electrons. Okay, it liberates electrons. Now what happens is this Zn2 plus, okay, that is this A plus, this Zn2 plus thus formed will be moving to the interstitial site. It will be moving to the interstitial site and an equivalent number of electrons are accommodated in the nearby interstitial site. Okay, so the electrons furnished here will be moving to the interstitial sites. Okay, the electron trapped electrons, that is entrapped electron in the interstitial sites, enhances the conductivity of this zinc oxide and imparts yellow color to this zinc oxide at high temperature. Understood, students? Actually, this type of defect is found in the crystals which are likely to exhibit Frenkel defect. Understood? So this is an example for the metal excess defect due to extra cation. Okay. And the last one is the metal deficiency defect due to cation vacancy. Okay, actually this defect arises due to the missing up of cation of lower valency and another site is occupied by a cation of higher valency. Understood? See here, this is a crystal in which this is having A plus and B minus, that is a cation and anion, cation and anion. Here one of the cation of lower valency will be missing and another site is occupied by a cation of higher valency. See, let me explain here. See, when a cation of higher valency is added to a crystal, see here, this is A plus, but a cation with extra positive charge means A2 plus. Okay, A2 plus. When a cation of higher valency is added to the crystal, two or more cations of lower valency has to be replaced to maintain the electrical neutrality. Is it not? See, when A2 plus is added, then 2A plus has to be replaced. It should give space. Okay, so the A2 plus is getting occupied here. So in order to maintain electrical neutrality, 2A plus has to be removed. Okay, it should move. Because of this, a cation valence vacancy will be created. Okay, a cation vacancy will be created. Understood, students? See, let me explain with an example, that is FeO, that is ferrous oxide. See, in FeO, what happens is the Fe2 plus cations are missing. So the loss of the positive charge is neutralized by the presence of the required number of Fe3 plus ions. Okay. So here extra positive cation is occupying the one of the vacancies, and obviously in order to maintain the neutrality, one more cation has to be removed so that there will be a vacancy created due to cation vacancy. So this defect is shown by the transition metal atoms capable of showing variable oxidation states. For example, FeO, FeS, NaO, etc. Understood, students? Well, fine, students, you might have understood the defects in non-stoichiometric crystals. I shall meet you with another important topic in a short period. Until then, it's Dr. Anita signing off from you. Thanks for watching.